Good old Ann. Plane turns a horizontal circle in 3 minutes. Nice try, Duick. First thing I did, Keegan, I crossed that out and I wrote 120 seconds above it. Hopefully you've picked up on little tricks like that from me as well. Lazy but organized is the phrase that I use. If the plane's speed is 170 meters per second, Keegan, what's A want me to find? Is there an equation? Do we have something that relates radius and speed when we're moving in a circle? What equation, oh pray tell? That's for an acceleration. I think there's another one that relates, oh, and also period, because I have time. Let's see. Do I know the circular speed? Yeah. Do I know the period? Yeah. Get the R by itself, please, Keegan. How will I move the 2 pi over? So I'm trying to get the R by itself. How will I move the 2 pi over? How will I move the t over? So I think it's going to be, R is going to be V times t divided by 2 pi. V, 170. Turn the calculator on, Mr. Duick. 170 times t, 120, divided by bracket 2 pi. Did you all get 3,250? I got a little nervous at first, and no, wait a minute. This is a big airplane doing a circle like a jetliner. Yeah, probably a circle would be have a radius of about 3 kilometers. That's probably, I'm okay with that now that I think about it. So 3,250 meters. I would give you 1 mark if I saw that, half mark for getting the R by itself, half mark for the answer. Keegan, what's B want me to find? Okay, can you give me an equation for centripetal acceleration? I can use V squared over R. I'll be using, let's see, they gave me a V, and I guess I'll be using the R from part A. Or I can use the 4 pi squared R over T squared. No matter what, I'm going to be using my answer from A, so I probably would have gone with AC equals V squared over R because it's the least amount of typing. 170 squared all over. I'll write 3,250, but you know I'm using my answer button. Did you get 8.9? Okay. Pulling about a G. Yeah, okay. I'm okay with that. In fact, I think it was 8.90. Yeah, it was. Okay. 1 mark, half mark, half mark. Did anybody use the 4 pi squared R over T squared? Could have. Okay, so same thing. I would give you 1 mark for writing the equation, half mark for the numbers. You would have got the same answer. Yeah. Okay. Nick, what's number 2 want me to find? The what force? The net force. Oh, sorry. This is centripetal force. I don't need to do a free body diagram. I can go straight to FC equals MAC. In the same way as last year, a what force, a net force, I can go straight to F equals MA. Centripetal force, FC equals MAC. Which version, Nick, of A am I going to use? The one with the V in it or the one with the T in it? The V? What's the speed then? Good. Good. You caught yourself? Okay, I know you're late, waking up. Okay, we're wakey. 4 days off. I get it. So I'm going to use don't forget the M. Common mistake, by the way, kids go like this. They go, oh, it's 4 pi squared R over T squared. Because, Nick, that looks so complicated. They think, surely that must be a force. It's not. It's an acceleration. F equals what? MA. Ooh, we got somebody 2 humans showing up. Pause for a second. So, Nick, don't forget the M. Hey, now it's plug and chug. What is the mass? Yep. And then it's going to be times 4 pi squared. What's R? 6 all over. What's the period? How long does it take to go around once? Don't forget the squared on the t. 12 times 4 times pi squared times 6 divided by 0.2 squared. Holy, is it 71,100 if I go to 3 sig figs? It's a force, so newtons. I got nervous when I saw that at first, but then I went, wait a minute, Nick, what's the mass in this question? 12. What's R in this question? 6 meters is about from me to Sarah, roughly. Okay? We're spinning a 12 kilogram mass, a bowling ball basically, around in a 6 meter circle every how many seconds? What's the period? That's 5 times a second you're spinning it around. Would that take a fair bit of force? Actually, I'm okay with this large answer now that I think about it. Yeah, this would kill you if you stood in the way and got the impact on your chest. It would shatter your whole torso. You would not want to have this hit you. This is a lot of force. Okay, so I'm okay with this answer. I would probably go something like this. Half mark if I saw that, half mark for that, half mark for the numbers, and a half mark for the answer. Okay. Emilio, what's number 3 want me to find? So I went AC, centripetal acceleration. Am I going to use the one with the T or the one with the V in it? Oh, they gave me speed? So just V squared over R. Oh, by the way, number 2 is worth 3 marks, not 2 marks. I was going, wait a minute, something seems wonky. So I guess I would probably do something like this. 1 mark, oh, change colors, Mr. Dewick. 1 mark if I see this, and 1 mark for the answer. But if you got it right, you get 3 marks. V squared over R, it's going to be 5 squared over, ooh, nice try, Mr. Dewick. 0.25 meters. You caught that, right? So it's going to be 5 squared all over 0.25. Is it 100 even? One mark, half mark, half mark. If you forgot to convert the centimeters to meters, you would have got 1 as an answer. I would give you 1 out of 2 and say, please watch your units. Next page over. Ferris wheel. Ferris wheel, roller coasters, this is going to be a job for a free body diagram. It wants the force the bench exerts on the person at the top of the Ferris wheel. I did a quick sketch. I said, there's the top of the Ferris wheel, there's the person. What are the forces acting on this person? Well, get the obvious one. Gravity. What else? Well, it wants the force the bench exerts. Lena, what's that code for? Which force am I asking you to find when I say the force that the bench or chair exerts? Normal force. Which way is the normal force? It's always going to be which way your head is pointing. In a Ferris wheel, you're sitting like that, and so your head is pointing up. And so the normal force is going to be pointing upwards. Bigger, smaller, or the same size as mg? And how do I know? So, okay, I'll exaggerate it. What path am I tracing out? A circle. Where is the bigger force going to be pointing? Toward the, which way is my acceleration? Toward the center. Which way is my velocity? Tangent to the radius. Okay, so now I've got my equation. It's going to look like this. Winner minus loser equals MAC. I want to get the normal force by itself. You know what? There's a negative. I'm going to do the swappy dance. I'm going to get mg minus mac. And if you don't mind, I'm going to put the normal force here by itself. Madison, which version of AC am I going to use? The one with the V in it or the one with the T in it? Oh, okay. So the normal force is going to be mg minus m 4 pi squared r over t squared. Do the m's cancel here? Do I have an m in everything? Don't have an m in the normal force. So, okay. Now it's going to be plug and chug. M 65. By the way, I clearly made an error here. I should have said the person has a mass of 65, because if I said weighs, that should be in newtons. If I say weighs, because I should have given you mg, I'll have to fix the wording of that, because things like that do irritate me. We didn't notice that, Mr. Dewick. What, that things like that irritate me, or the weight, or both? Minus 65 times 4 pi squared r9 all over 25 squared. I have no idea what the answer here is. 65 times 9.8 minus 65 times 4 pi squared times 9 divided by 25 squared. Double check for typos. 4 pi squared r over t squared. Don't forget the... You get 600 even? 600.05. I'll go 600. If you got that, 3 out of 3. Otherwise, 1, 2, 3, 4. I would probably go something like this. A half mark if I saw that line. A half mark if I saw that line. A half mark if I saw that line. A half mark for the numbers. And then 1 mark for the answer. Ooh, bottom of the Ferris wheel. You know what? It's going to be really, really similar, but I think it's still a job for a free body diagram. What are the forces acting at the bottom? Get the obvious one. Gravity. What else? Normal force. Which way is the normal force going to point, Quinn? Is it going to be bigger, smaller, or the same size as mg? And how do I know? What path are we tracing? I'll really exaggerate it so it catches my eye. So here it's going to be normal force minus mg equals mac. It's going to be normal force equals mg plus mac, or mac plus mg. It's going to be normal force equals mg plus m 4 pi squared r over t squared. It's going to be mg plus 65 times 4 pi squared times 9 all over 25 squared. I was clever. I noticed, you know what, Mr. Dewick, if you just backspace on your last entry and change the minus sign to a plus sign, none of the numbers have changed, so I did that. 674 newtons. Same as before. Half mark, half mark, half mark, half mark, 1 mark. Ooh, roller coasters, roller coasters. Okay. Oh. Claudie, what's number 5 asking me to find? How fast? I thought maybe about conservation of energy, but first I went, oh, what path are we tracing out? I think I'm going to figure this out maybe by using centripetal force, which just means it's probably a job for the free body diagram. What are the forces acting on this person on the top? Get the obvious one. What else? Normal force pointing which way? Also down. Because that's the direction your head is pointing. Who's winning? They both are. So my equation is going to look like this. mg plus fn equals mac. Actually, I said, you know what? They're asking me to find how fast. I'm clearly going to use the v squared over r. I could get the v by itself. It would be times everything by r in brackets divide everything by m square root. This is about where my love for formula manipulation, Jan, ends. What I'm going to do is I'm going to turn this into one number. Then I'll get the r by itself. So I said I'm going to drop the mg down, plus, I don't know the normal force. Or do I? Claudie, what did it say the normal force is? 4.5 times their weight. How would I write that? I'll give you a hint. There's going to be a 4.5. Or if I'm just doing my equation times mg equals mv squared over r. Here's where I noticed something. First of all, is there an m in everything? Yeah. Everyone's going to feel 4.5 times their weight, whether they're a small kid or a grown-up. I also said, you know what g plus 4.5g is? I gathered like terms. Now some of you might already have started to put numbers in, but I noticed I can write this as 5.5 g's equals v squared over r. And the reason I did that is, how would I get the v by itself? How will I move the r over? The r, and then what? And I smiled because I saw I was getting a square root of GR and other stuff, but I was like, I'm probably doing this right. So I went, okay, r is going to be 5.5 r, Mr. Dewick, v, getting the v by itself, it's going to be 5.5 GR square root. So I went, I'm probably on the right track. Um, 11. Now, if you didn't cancel out the m's and gather like terms, you're fine. You should end up with the same answer as me. 5.5 times 9.8 times 11. Did you all get 24.3 meters per second? If you got that, I would give you 4 out of 4. Otherwise, I would probably go something like this. 1 mark for that, half mark for that, half mark for that, or if you started plugging in numbers, half mark if you got that, half mark for the answer. What am I at? 1, 2, 3, and so for the numbers, probably 1 mark for the answer, something like that. After the first loop, the riders hit a second loop. At the top of the second loop, okay, there's the top of the loop. The rider is traveling at 16 meters per second, and they feel a normal force of twice their weight. What's the radius? Okay, I guess this is asking me to get the r by itself. Still going to be a job for a free body diagram. mg and normal force, both pointing down. In fact, it's still going to be mg plus fn equals m. And since they gave me a v, I went v squared over r. I said it's going to be mg plus, the normal force is twice their weight, 2 mg's equals mv squared over r. I noticed, yay, the m's cancel. If you didn't, that's fine. I ended up with 3 g's equals v squared over r. I want to get the r by itself. Where is the r right now? On the bottom. Ugh. But I said, wait a minute, this is technically 1 fraction equals 1 fraction. Stuff moves diagonally. I didn't bother writing the 1, I just imagined it there. So the r can move to the top on the left, and the 3g will move to the bottom on the right. I said, I think we're going to get r equals v squared over 3g, which is going to be 16 squared over 3 times 9.8. And I get 8.71 meters you got that, 4 out of 4. Otherwise, again, I'd probably give you 1 mark for the initial setup, half mark, half mark, half mark, half mark, and then 1 mark for the answer. Can you give yourself a lovely score, please, out of 23? If you need to lawyer with me, now is the time. Look at take-home quiz number 2, please. Not a very long quiz. So number 1, a car going around a corner barely negotiates a circular turn. If mu equals 0.655, how fast is it going? So this is the car going around a corner question. A 2.5 gram spider sits on a platform rotating with a period of 0.682 seconds. The spider is 19 centimeters from the center of the disk. Find the speed of the spider. I think this is the same physics as number 1 because I think in both of them it's friction that's making you go in a circle, whether you call it the tire's friction or the spider's grippy feet. And then B says, find the friction coefficient necessary to keep it in place. I think you will find that it has a mu bigger than 1, and that's because spiders can stick to objects beyond just friction. They have sticky feet. Then if you turn the page over, here's a gravitron question. If you turn the page over. There we go. Okay? There's going to be a gravitron on your test. You'll get some time later on in class to work on it. But for now, let's move on to the final lesson of the unit. Lesson 5, I called this Cool Applications. Roller coaster loops. How many of you have ever been on a roller coaster with a circular loop? Raise your hand, please. Put them down. How many of you have ever been on a roller coaster with a circular loop? Raise your hand, please. Put them down. How many of you have been on a roller coaster with a circular loop? None of you. The reason I know none of you is you're not dead. We do not build roller coasters with circular loops. You may think we do. We don't. And here's why. Example 1. A roller coaster. I am not going to ask you a question this tough, but this is just some cool physics, and it's a great review of everything. But you will not get this specific question on your test. Read along with me, Janet says this. A roller coaster barely makes it around a vertical loop of radius 4 meters. A says, find the minimum height that the roller coaster needs to start from at the top of the hill. Cohen, what's A asking me to find? Height. Okay. Any suggestions on what we might try? Maybe conservation of energy. So, okay. Is there a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky curvy path? Maybe. This looks straight, but it might be wiggly and I see kind of loops. I think I'm going to try conservation of energy, but here's the key. I'm going to let initial be right here. I'm going to let final be the top of the loop. Because this is asking, or this is saying the roller coaster barely makes it over. Okay? So, here we go. And I guess what they want us to find is that. So let's write out our conservation of energy. It's going to be Ke initial plus Pe initial equals Ke final plus Pe final. Cohen, are any of these 0? Well, if it wants the minimum height, then let's assume we're starting at rest. Because we want to find how high we need to be. At least if we had some extra energy, we could start lower. But if we're starting at rest, this is the minimum height we have to have. Is our initial potential energy 0? No. What about our final kinetic energy at the top of the loop? Can't be, because if we came to a stop, what would happen? Okay, so that can't be 0. What about our final potential energy at the top? No, we're at the top of the loop. Down here, maybe, but not at the top. Okay. Well, let's go further. This is going to be mgh initial plus, not plus, equals a half mv final squared plus mgh final. Cohen, can little kids and grown-ups go on this roller coaster together? Why? Oh, that's convenient. What are they asking me to find? Well, eventually I'll get the HI by itself, but I'm going to pause for a second. I could divide by G. Hold on. Do I know the speed right here? You know what? This is a job for a free body diagram. I'm going to do a free body diagram and workings over here. I'm going to label the picture. At the top, Cohen, what are the forces acting on this coaster? Get the obvious one. What else? Which way? Write me an equation for that. MAC, yes? Oh, you know what? How about this? V squared over R, because I'm trying to find V there. What word did I underline? What we're saying by that, barely, is we're saying the normal force at the top is 0, because that's, we played around with this, that's the slowest you can possibly go and still make it over. And so what we get is this. mg equals mv squared over r. Oh, little kids and grown-ups still okay? Okay. I'd like to get the v by, wait. Actually, I don't want to get the v by itself. You know what? I want to get the v squared by itself. So why don't I just do that? I could square root, but then I'd square it later, Madison, so why bother? Cohen, how would I get the v by itself? Okay, how would I get the v squared by itself? Then just GR. And this is v final at the top. So what I can do is I can replace it right here. So underneath, we'll drop down a line. We'll get GH initial equals, there's a half, a 0.5. But instead of v squared, Alex, I'm just going to write GR. Because if v is the square root of GR, then v squared is just GR. Plus, and I'm going to write the G. And I'm going to pause again. Not going to write H final. Cohen, what do I call that distance right there? What letter have I used for radius? Okay, so Cohen, ready? How far from here to here? What did you just say? What letter? Again, how far from here to here? How far from here to here? How far from here to here? So here's my question. In terms of R, what's the height? In terms of R, what's the height? How far from here to here? What? What? Do you see it? The height of this roller coaster is twice its radius. Fair enough? So instead of writing H right here, I'm going to put in 2R. Oh. Quinn, is there a G in everything? What does that mean? We've had G occasionally canceled. Does anybody remember what that meant? So, this would work on any planet. What it's telling you is if you could set up this same identical coaster on the moon, the car would still make it through the loop. You set up the same coaster on Mars, the car, assuming you could overcome logistical issues of people dying, in a vacuum, but the car itself would still make it over the loop. Okay? And we get this. H initial is 0.5 R plus 2R. Oh. Don't go to your calculator yet. What is 0.5 R plus 2R? Those are like terms. Cohen? What's 0.5 R plus 2R? What's 0.5 R plus 2R? Sorry? Did you come up with that, or did Reed whisper to you? Okay, so I love that answer. I'm not saying I like this question, I like this question, I like this question. But Lena, I love how, look at all the complicated stuff we started with, and then things just started canceling left, right, and center. This is the coaster equation. I'm going to guess any ride designer has this one memorized. In the same way all of you have memorized the 9.8, they would know if I'm building a circular coaster, I've got to make sure that my first hill is at least 2.5 times the radius. Otherwise, we're not going to make it through. And now, Cohen, I'll even bet you can do this in your head, because it's going to be 2.5. What was the radius as a number exactly? You didn't go to your calculator, did you, Cohen? You did? Fine. Using your calculator instead of your brain, what's 4 times 2.5? Really? For this specific coaster, it's 10 meters. Don't turn the page yet, Keegan, because there's a part B. Okay. So let's put a little part A right here. B. Mallory, what's B want me to find? The normal force. Where? Scribble, scribble, scribble. There's final. Bottom of the loop. I put the F down here now. Got rid of the F up there. Right? Lazy but organized. So final what was at the top for part A, it's at the bottom for part B. What does it want me to find? Well, this is a job for what are the forces acting at the bottom? Get the obvious one. What else? Bigger, smaller, or the same size as mg, and how do I know? Why? We're past, okay. Tracing out a circle. So I guess I'll have this. Normal force minus mg equals mv squared over r. And I knew to go with the v squared over r because this question doesn't mention the period, but I think I can find speed using conservation of energy. Get the normal force by itself. Problem. I don't know the speed. Wait a minute. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? I can figure out the speed here. It's going to be conservation of energy. So it's going to look like this. Ke initial plus Pe initial equals Ke final plus Pe final. We already said we're starting from rest, Mallory, so we can do that. Oh, where is my final in this part, in part B? Where did I put the F? Cross out PE final. And Mal, I end up with this. A half mv initial squared. No, Mr. Dewick. Jeez, that's the wrong equation totally. How about mgh initial equals a half mv final squared? Oh, Are we still okay with little kids and grown-ups? What can I replace my initial height with? This is going to be G times 2.5R. That equals V squared over 2. I turned the 1/2 into a 2 on the bottom. Mallory, get the V by its... Actually, you know what? There's a V squared in the equation over here. Let's get the V squared by itself. How will I move the 2 over? I'm going to get this. V squared equals 2 times G times 2.5. You know what? V squared equals 5 Gr. Mallory, put your calculator down. I like your enthusiasm. I'm going to stick that in over here. When I do that, there's going to be an M. Instead of V squared, I'm going to write 5 Gr all over R plus mg. Sarah, you went, oh, what did you see? Oh, I thought you had a little realization there. Sarah, is there an R right there? Is there R on the bottom? Here's what I end up with. I've kind of gone all over the place messy because I'm trying to hit this all on one page. I end up with the normal force is going to be 5 mg plus mg. What's 5 mg's plus 1 mg? I can gather like terms. Now you can go to your calculator. What was the mass? 75? What was the mass? 50, sorry. Do you get 2,940? Okay. Quinn, what's C want me to find? Oh. How many G's is this person pulling? You can see it actually right here. Look, 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 look. No calculator. How many G's are they pulling? What's your norm? Yeah. You've done enough physics. Is 6 G's very healthy? No. This is how I know none of you have been on a circular loop. The very first roller coaster loops, Nick, that they built were circular. In fact, the first one, it wasn't actually a coaster. It was like a water slide, but for mine cars, for little tiny cars you got in. And all you did is you climbed a big set of stairs. You got in at the top. It went whooshing down. At the bottom, there was a loop, and you got off. They had permanent ambulances and nurses stationed at the bottom, and yet people loved it. They just went on it like, this is just the best, but people regularly got whiplash, got injuries, because 6 G's is a lot. Nobody builds circular loops. What you build instead, this is just nerd trivia, is what's called a clothoid loop. A clothoid loop looks much more like a teardrop. The fancy expression, it's a loop of ever-decreasing radius. And by doing that, you dramatically reduce the amount of G's you're pulling at the bottom, because look at how gently you're pulling out instead of pulling out sharply. Okay? If you look at a roller coaster loop from the side, you'll see they look much more like this. How many of you have been on what used to be called California Screaming? I think now it's called the Incredicoaster. Okay. That's got a loop. If you look at that loop, it looks nearly circular. It's not. It's an optical illusion because they put a big a picture of Mickey behind it to help reinforce the illusion, and they actually distorted Mickey's picture to help reinforce the illusion. But you do pull a fair number of G's at the bottom of that one. That one, whenever I go on it, I'll do one of two things. I'll either try and lean forward and at the bottom see if I can straighten myself out. I can't. It's a lot of G's. Or I'll just hold my arms out and just do this at the bottom of the loop, and you can feel the G's acting on you. It's kind of fun. But yeah, in a roller coaster loop, they're never circular, because if they were, well, first of all, you would need to have the initial height 2.5 times the radius. That's fine. But you'd be pulling 6 G's. We don't do that. Turn the page. Number 1 and number 4 are fair game. Let's take a gamble and see if I get a takedown notice for the videos. Put your pencils down, look up. Come on, computer. So we're done the lesson, we're done the unit. I have an interesting video to show you, or you can work on the take-home quiz and the homework. What was it? 5th gear, Mr. Dewick.
Welcome back. Right, I'm really excited about this next item because it's the biggest and bestest thing 5th gear has ever done.
Hell yeah, check this out. Who remembers these? Hot Wheels Loop the Loop. Come on, Tom, someone down. There we go. Yes, but what we wanted to know is, can you do that in a real-life family-sized car?
Yeah, we gave the job to our friendly neighbourhood stuntman Steve Trulia, but we wanted some questions answering first. How fast would he have to go? Would the car stick to the road? And would he black out under the G-forces?
Steve Trulia is the man facing this monster challenge. As 5th Gear's head of danger, he's rolled, crashed and crashed again in numerous 5th Gear stunts. But even by these extreme standards, nothing can prepare him for our most dangerous stunt yet. Clearly, scaling a toy up to a record-breaking 40 feet high using 5 tons of steel and a real-life motor was going to be dangerous. So we sent Steve to Cambridge University's Dr. Hunt to find out how fast he'd have to go. Now listen carefully.
2r plus a half v in squared.
Starting to cook my brain a bit now.
36 miles per hour. But you know what we haven't worked out though is what are the G-forces you're going to experience? If you want to know whether you're going to black out or not, the total G-force you will experience as you enter this loop will be 6.
How many G's? We could have done that. If you looked at the workings he was doing on the board, exactly what we just went through with the circular loop for the roller coaster. The only issue is he's not using a hill to generate the speed, but he did find out what you needed your speed at the bottom to be to make it over the top. Yeah, he went through the same math.
Gives me a bit more confidence because of the science. But at the end of the day, I don't know if that's going to count when I'm staring at the track with my foot in the accelerator.
To lessen the chances of Steve letting out some wheel, he needed to get used to pulling 6G. The only place to do that was in this. Here we go, into the loop! Here we go, into the loop! 1, 2, pull it! 2, pull it! 2, pull it! Stunt Day. The day 5th Gear finds out if you really can drive a car around a 40-foot high loop the loop. If successful, stuntman Steve Trulia will set a new world record.
Spoiler alert, something almost goes
If he
wrong.
fails and falls out of the loop, the massive deceleration forces as he hits the ground could be fatal. The entry speed is therefore literally a matter of life or death. So Steve verified the car's speedo with GPS. 37, and then checked again with a calibrated radar gun. 36 miles an hour had been calculated as the ideal entry speed. Slower than this, and he'd fall. Much faster, and the G-forces would knock him unconscious and exert a dangerous force on the ramp structure. The Toyota Aygo Steve had chosen for the stunt had been heavily modified to make it strong enough and hopefully safe enough should things go wrong.
Here we go. This is it, we're going too fast. Here we go.
Did you see the issue? Watch the rear bumper on entry and exit. He bottoms out and starts to drag. The suspension wasn't strong enough. And had he dragged a little more, he would have not had enough speed at the top.
I'm so glad that I saved the road all the way.
Watch right here.
As soon as I left the road, complete feeling of joy and elation.
Dr. Hugh Hunt's analysis revealed how close we'd come to disaster. Just 2.5 miles an hour slower, and Steve had fallen.
And here we go.
1 mile an hour faster, and the extra friction caused by the scraping would have made him fall as well. Steve hits it spot on, so take a moment to savour the world record for driving a car around the largest loop-the-loop. Chances are you'll never see it executed so perfectly ever again.
Okay, so can a car go through a loop? Yeah. Here's the next question. How many of you have ever seen a full pipe at a skate park? Not a half pipe, but a full pipe. And so skaters going fairly fast, some of them can do the full loop. Could a running human being do it? Where is it, Mr. Duke? Good gosh. Got to pause for a second.
Good demo.
So, can you run a loop-the-loop as a human being? Oh, apparently drink Pepsi Max.
My name's Dane Walters, and I'm a stuntman who does tumbling, gymnastics, and parkour. I'm attempting to run the loop. I've seen people do it on a skateboard before, I've seen people do it on a BMX before. No one's ever tried it on their feet, so it's really nice to be the first guy to actually run it. It looked a lot bigger than what I thought it was going to be. Yeah, it must have been not the easiest thing ever. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further. See how far people can go.
Basically boils down to the centripetal force. You need to keep on accelerating.
I recognize that equation.
So you need to reach a certain speed. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour. That's it.
Okay. 3, 2, 1, go. 17.
So he can run at 17 miles per hour. It's pretty fast. He only needs 8.6. So in theory, totally doable. The physics says you can. The question is, can you actually do it?
reassuring that one back. Well, this one's it. I know I've said that 3 times now, but this one is it. I'm close, I reckon I'm close. Getting close. You can't really go any further until you take the match out. Let's get rid of it. Let's go for it.
Because the big challenge here, of course, when you're running uphill, you want to lean forward to keep your balance. What he's got to force himself to do, Nick, as he hits that loop, he's got to force himself to throw his body backwards in midair with nothing underneath him. But that's what will help him get his feet up and over and around. So he's having to really just overcome a lot of not completely clean, but we'll give him credit. I guess drink Pepsi Max. There's your commercial. So can you run a loop? Oh, don't try that yourselves, please. That's a professional. And one thing I would say, I'm a little stunned he wasn't wearing a helmet. I would definitely have worn a helmet, if nothing else. So